Here is another example of calculating the exact area using the limiting process. So here we have the equation y equals x cubed on the closed interval from 1 to 3, and we are supposed to find the area. Okay, so first thing we'll do is go ahead and sketch the region. So we're looking at x values going from 1 to 3. And when we plot these, if we plug in x, or if we plug in 1 for x, we get that f of x is equal to 1. If we plug in 3, we get that f of x is equal to 27. And we know the general shape of our curve. It's a cubic function, so it's going to look something like this. Okay, so here's the area in question. So we know that the area is going to be equal to the limit as our number of rectangles approaches infinity of the sum of all rectangles, where a sub I represents the area of each rectangle. So a sub I, again, that's equal to each base times each height of our rectangles. And our base of our rectangle is always equal to delta x. And delta x in this case is 3 minus 1 over n, which is 2 over n. And our height is always equal to f of left endpoint of the interval plus I times delta x. Okay, so for this one, we're going to have f evaluated at 1 plus our delta x was 2 over n, so this would be 2I over n. Okay, so next we're going to go ahead and let's evaluate this f at 1 plus 2I over n. So we're plugging that into y equals x cubed. So we really need 1 plus 2I over n, all being cubed. So now we're going to go ahead and use our Pascal's triangle to help us expand this expression out. And when we expand that out, we end up with 1 plus 6I over n plus 12I squared over n squared plus 8I cubed over n cubed. And that's going to be our heights of each of our rectangles. Okay, so now we can go ahead and plug that in for our area formula. So our area, again, will equal the limit as number of rectangles goes to infinity of the sum of all of our rectangles. And the height of our rectangles, we're using 1 plus 6I over n plus 12I squared over n squared plus 8I cubed over n cubed times the length of the base of our rectangles, which we said was 2 over n. Okay, so the hard part is done. Once you get these problems set up, these are not Once we get these problems set up, these are not that difficult to do because from here until the end, we basically just have a big algebra problem. Okay, so the first thing we're going to do is go ahead and distribute the 2 over n, and I'm going to use my property for sums to split that up into 4 separate sums. Okay, so when I do that, I get limit as n goes to infinity. For my first sum, I'm going to have 1 times 2 over n plus my second sum will be 6I over n times 2 over n plus my third sum, which will be 12I squared over n squared times 2 over n plus my third sum, which will be 16I cubed over n to the fourth. Okay, now I know that I want to rewrite these sums in terms of just the i's so that I can use the I formulas to replace the sums. So doing that, I'm going to pull everything that's not an I out to the front of the summation sign. So that gives me limit as n goes to infinity. For my first sum, I can pull out the 2 over n. I'm left with just the sum of i's from 1 to n of 1. Plus my second sum, I can pull out 12 over n squared times the sum, and I have just I. Plus the next one, I can pull out the 24 over n cubed times the sum of I squareds. And then my last one, I can pull out the 16 over n to the fourth times the sum of all I cubes. All right, so next I'm going to go ahead and replace each of those with the formulas for the sum of the i's. So now I get limit as n goes to infinity. For my first one, I have 2 over n times the sum of 1, so that's just going to be n, plus 12 over n squared times the sum of all i's, which is n times n plus 1 over 2, plus 24 over n cubed times the sum of I squareds, and that one is n times n plus 1 times 2n plus 1, all over 6, plus 16 over n to the fourth times the sum of I cubes, and that one is n squared times n plus 1 over 4. And this n plus 1 should be a square. All right, so now I go ahead and do my canceling out. And let's see, I have an n times or an n over n, we can cancel those. In my second term, I have a 12 over 2, which I can simplify to 6 over 1. I have an n that will cancel out an n. I have 24 over 6, so that'll simplify to 4 over 1. I have an n factor here that will cancel out an n here. And then in my last term, I have 16 over 4, so that will simplify to 4 over 1. And then I have an n squared, which will cancel out n squared on the bottom. Okay, next I'm going to go ahead and multiply everything that's left, multiply that out, because then I can divide term by term. So here in the term here with the n plus 1 times 2n plus 1, we can go ahead and FOIL that out. So 2n squared plus 3n plus 1. And then n plus 1 quantity squared, that's the same as n squared plus 2n plus 1. Okay, we are almost done. Go ahead and divide term by term, and then we'll take a limit. So we have limit as n goes to infinity. I have left over here, I have 2. In my second term, I have 6 times n over n. So that is just 6. And then I have 6 times 1 over n. So that's 6 over n. Next term, I have 4 times 2n squared, so 8n squared divided by n squared, so that's plus 8, plus 4 times 3n, that is 12n, divided by n squared, so that would be 12 over n. And then I have 4 times 1 over n squared, that gives me 4 over n squared. And then my last term, I have 4 times n squared over n squared. So that gives me plus 4. And then I have 4 times 2n, so it's 8n over n squared. That will give me 8 over n. And then I have 4 times 1 over n squared Yep, gives me 4 over n squared. And now finally I can go ahead and take that limit, and all of these terms that have an n in the denominator, n is going to infinity, so those will all go to 0. And what do I have left over? I have 2 plus 6 plus 8 plus 4, so that's going to give me 8 and 8 is 16 plus 4, so that is 20. So my area is equal to 20, and then squared units of whatever that is. Okay, so hopefully that'll help you out with the problems that you will be doing on your own tomorrow in class.